I represent here the computer department at the Alex Hanchat Dnipro National University. I would like to familiarize you with our work using the Elman neural network as an identity map in defect detection task by authors Vladimir Handetsky and me, Nadia Karpenko. At present, in a number of industries, composite materials are widely used due to their high mechanical and thermodynamic properties at low density. Most of them are laminated materials, so the most common defect in them is delamination. With two-sided access, it is reasonable to use an ultrasonic shadow testing method with the radiating and sensor elements located on opposite sides, for example, the product wall. Delamination of the material is a barrier in the path of ultrasound. A composite material is heterogeneous in structure. The spatial arrangement of reinforcing elements, such as fiber bundles, is also not ideal. In the bulk of the material and on its surface, especially at fast boundaries, there are accumulations of pores and various kinds of micro-defects. Cracking of the composite matrix and fibrous breaks are observed. The concentration of micro-defects is especially high at the boundaries of delamination. All this structural imperfection distorts the defect image fixed by the sensor element. Therefore, to identify the defect and estimate the true area of the delamination, it is necessary to process its noisy image. The article aims to create an intelligent system with a core in the form of an Elman neural network to identify and estimate the area of distorted defect images moving within the control zone. In the process of solving this problem, we want to study the ability of recurrent neural networks to identify dynamic noisy images of various sizes defects in the process of scanning by the measuring transducing the product surface. In our case, the control zone of the ultrasonic transducer is displayed in the form of a square matrix of 100 by 100 elements. The Elman network, which performs image processing, has 100 inputs and 100 outputs. We use this network as a replicator or identity map. The network is fully connected. The results of calculations of the number of neurons in the hidden layer are shown that the optimal number equals 200. In accordance with Wederow's rule, the size of the training set necessary for a good generalization should be, in our case, of the order of n equals 10 raised to the 6th power. We used 8,967 clean and noisy images for training, but each of them is repeated 100 times within the same epoch. Thus, the actually used volume of the training set is 896,700, which is close enough to n. The image of the defect delamination has the form of a continuous black spot, which is formed by the n-matrix cells with a color level L equals 5 adjacent to each other. This spot is surrounded by a layer of gray cells with L equals 4. The next layer of cells corresponds to L equals 3 and so on to L equals 1, white color. The defect image pattern number 1 is a black square with a size 2 by 2 cells. Moving this image on a matrix of 10 by 10 cells is carried out line by line. In patterns number 2 and number 3, the left and right upper cells of the black square are replaced by gray cells with L equals 4. Image number 4 is a black square with a size 3 by 3 cells. For patterns number 8 and 9, in the upper layer, 2 cells on the left and 2 on the right are replaced by gray ones. Image number 10 is a black square with a size 4 by 4 cells. Patterns number 11, 12, and 13 differ from the target pattern number 10 by the alternate replacement of each of the black corner cells, with the exception of the checkpoint on the gray. Patterns number 14 and 15 are formed similar to patterns number 8 and 9, only for the target image number 10. Image number 16 is a black square of 5 by 5 cells. Patterns number 17, 18, and 19 are formed similar to patterns number 11, 12, and 13, only for this target image. For images with the next numbers, a pair of cells of the outer black layer shifting along the periphery of the spot is replaced by gray ones. The defect images described above were noisy. The absolute noise level P was set by us as shown on slide 6. Noise is additively mixed with a clean image. We used the levels P equals 10, 30, 50, 70, and 90. The full image contains cells with gray color gradation from L equals 1 to L equals 5. We assume that distribution of the distortion magnitude delta L equals 1, 2, 3, 4 by the number of distorted image elements is Gaussian with a zero mean value and a standard deviation equal to 1. The relative noise level gamma we calculated as shown on slide 6. For example, gamma equals 31% corresponds to 72 cells with delta L equals plus or minus 1, 16 cells with delta L equals plus or minus 2, and 2 cells with delta L equals plus or minus 3, and so on. The functional scheme of the intelligent system is shown on slide 7. In the center of matrix that represents the control zone of an ultrasonic transducer, there are positioned defect images capture zones. These zones correspond to images number 1, number 4, number 10, and number 16, which are targeted for the classes 1 to 4 correspondingly. The logical matrix inputs are numbered in accordance with the pair JK, where J denotes the row number and K denotes the column number of the matrix. The Boolean functions f1, f4 implemented as the corresponding outputs of the logic matrix are shown on slide 8. The analysis of expressions for f1, f4 shows that the patterns described by them are sequentially nested one into another. Thus, then fixing an image of a senior class, for example, number 16, the logical unit will be present not only at the output f4 of the logical matrix, but also at outputs f3, f2, and f1. The combinational circuit helps to eliminate this effect. This circuit realized in the classical basic of logic elements and provides separate fixation of each class of image. Herewith, the appearance of a logical unit at one of the outputs D1, D4 of the combinational circuit indicates the capture of the defect image of the corresponding class. Figure on slide 9 shows a graph of the dependence of the training time relative to one clean pattern alpha on the area of the defect. Training time for noisy images relative to one pattern beta is significantly less. So, for images of the first class, the ratio of beta to alpha is equal to 0.045. For the second, third, and fourth classes, we have 0.027, 0.032, and 0.021 correspondingly. A network testing with the maximum noise level gamma equals 31% has provided the following. If testing was carried out after a full cycle of network training on patterns of any one class using then a noisy image from the same class, then the test error did not exceed 3%. Finally, we have made the following conclusions. With the expansion of the defect spot area range from S equals 3 to S equals 9, the testing error increased to 8%. From S equals 3 to S equals 25, the testing error increased to 12%. With a reduction in gamma from 31 to 27%, the testing error decreases by 40 to 50%. With a reduction in gamma from 31 to 22%, the testing error decreases by 60 to 70% and so on. The above results were obtained by using the Elman neural network with the number of input and output neurons equal to 100, the number of hidden neurons equal to 201 layer. An increase in the number of neurons in the hidden layer to 400, on average by 25% reduces the testing error. However, the network training time increased by 30%. A network with two hidden layers, while reducing the test error by 20%, training 4 times longer than a network with one hidden layer. Training a network with 3 hidden layers took 14 times more time than the single-layer network we used. Therefore, the structure and parameters of our network are optimal. Estimation of the defect area serves as the basis for determining the residual strength of a given unit of a product and making a decision on the possibility of its further operation. Thanks for your attention.